Okay, so 2.36, we are given the infinite square well, but instead of going from 0 to a, it's now centered at the origin and goes from negative a to a. We want to check that the resulting energy and wave function that we get is consistent with the standard one for the 0 to a infinite square well. And we want to check that sort of the only difference is that we end up substituting x with x plus a over 2, and also we're told as a hint that the width of the well is now 2a as sort of a thing to watch out for. So for reference, the energy of an infinite square well back in the earlier section, way back in 2.2, was defined as E sub n is equal to h bar squared times n squared times pi squared over 2ma squared. And we also showed that the wave function was equal to the square root of 2 over a multiplied by sine of n pi x over a. So for reference, what we're being told now is that we want to basically replace all of the x terms with x plus a over 2, and we want to replace sort of the a terms with 2a. So let's try that. So immediately, for sort of the first thing that we should expect is that the general form for the wave function stays the exact same, because all the potentials and systems stay the exact same. So we still accept, or we still expect a sinusoidal sort of wave function. So we still expect psi of x to look something of the form of a sine kx plus b cosine kx, where k is equal to the square root of 2me divided by h bar. This still stays the same, just like in 2.2 when we derived this expression. Now, if we realize that this is an infinite well, immediately that means that the derivative no longer has to be continuous. So we only have the boundary conditions being that psi of x itself has to be continuous, not its derivative. So our two positions are at x equals negative a and x equals positive a. So what we have is that they both have to equal 0 because the potential goes to infinite outside of the well. So we have a sine of negative ka, which is going to be negative a times sine of ka due to the oddness of sine, plus b cosine negative ka, which is just going to be equal to ka because cosine's even, and this is going to be 0 at x equals negative a. And then at x equals positive a, we have a sine ka plus b cosine ka, also equaling 0. So if we actually solve this out, this gives us two possible different boundary conditions, because we can either add these two together. So if we add these two together, then the a's cancel out and we get 2b cosine ka is equal to 0. Alternatively, if we subtract these two, then the b's cancel out and we get 2a sine ka is equal to 0. And both these conditions are valid. So this results in sort of two possible sets of conditions, both of which are sort of equally valid to solve this system with. Either, so we either have ka is equal to n pi and b is equal to 0 in the a term, in the a case, because if ka equals n pi, then the sine term is always going to equal 0. But if ka is equal to n pi, then while the sine term goes to 0, the cosine term never does, so b by necessity has to equal 0. Or we can do the opposite, we can have the cosine term equal 0. So in that case, we get ka equals n plus 1/2 pi. So that way, the cosine term always goes to 0. It doesn't matter what b is, but because of that, the sine term will never go to 0. And a by necessity has to equal 0 now to make the sine term go to 0. So these are our two valid solutions. If we actually wrote them out for k, then we get that k is equal to n pi over a, or k is equal to n plus 1/2 pi over a, where n is equal to 1, 2, 3, etc., etc., etc. So this is where sort of the first tricky part comes in, because this sort of solution sort of implies that the width of the well is still just a. Because remember, the hint we gave was that note that the width of the well is now 2a. So to sort of represent this, we actually want to have a 2a at the bottom instead of just a. Because if we just have a at the bottom, then our solution kind of looks like the infinite square well case in 2.2, where the width of the well was only a. So I can technically multiply both sides by 2 over 2, and I get that k is equal to 2n pi over 2a, or k is equal to 2n plus 1 pi over 2a. And this is more sort of akin to what we actually want, because now we have a 2a at the bottom that suggests that our well actually has a width of 2a instead of just a. Now, recognize that, n is an index, so I can absorb constants into the index without any problems. So if I do that, then I can rewrite this as just k equals n pi over 2a, where n is equal to, even numbers only, so 2, 4, 6, blah, blah, blah. Or, on the opposite side, k is equal to n pi over 2a, where here it's 2n plus 1, so n is always odd, so then n is going to equal 1, 3, 5, etc., etc., etc. So what we're seeing is that the two sets of solutions that we have correspond to exactly half of the solutions. We have all of the even indexed solutions coming from the sine expression, and all of the odd indexed solutions coming from the cosine expression. So at this point, we have effectively gotten all the valid energies, because if we remember that k is equal to the square root of 2me divided by h bar, then, we say, okay, well, in that case, n pi over 2a is equal to the square root of 2me over h bar. And then if we redefine this in terms of e, we get e is equal to n squared pi squared h bar squared over 2m times 2a squared, which, if we compare with the energy up above here, the only thing that changes is instead of a squared, it's now 2a squared, which is what we expect because the width of the well is now 2a. Now, the next thing we can do is we can look at the wave function. So if we look at this general wave function, now we actually want to solve it. And to do that, we have to sort of first normalize everything. So to undergo normalization, we have to sort of start by redefining b in terms of a or a in terms of b. So I can say, from here I can say, okay, b cosine of kx is going to equal, or ka, I suppose, is going to equal a sine of ka. So in that case, b is equal to a times sine of ka over cosine of ka. So in that case, the general solution is going to look like psi of x is equal to a sine kx plus b times cosine kx, where b is going to be equivalent to what we defined here, a times sine of ka over cosine of ka. So then we can sort of take the magnitude squared of this to find a. So if we recognize that, let's see. If we take the magnitude squared of this to normalize, then we get a squared times sine kx plus cosine kx times sine ka over cosine ka squared. So at this point, let's see. From here, I can multiply cosine ka over cosine ka, and this is going to give me that a squared times sine kx cosine ka plus cosine kx sine of ka squared. And this is equal to magnitude psi squared. Let me just rewrite this. Okay. So at this point, I can take advantage of trigonometric angle addition properties, because realize that, sine A cosine B plus cosine B sine A is equal to sine of A plus B. So this is actually equal to a squared times sine squared of k times x plus a. And this is equal to magnitude psi squared. If we then take the integral, then we have our integral from negative a to positive a squared at the left times sine squared k x plus a dx is equal to 1, and then we can normalize this. So to do this, we're going to have to use double angle formula. So let me just pull that up. Right, so double angle tells us that, where did my pen go? There we go. Okay, right. So double angle is going to tell us that cosine of 2 times the argument, so 2k x plus a is going to equal 1 minus 2 sine squared of k x plus a. So that means 2 sine squared k x plus a is then going to equal 1 minus cosine 2k x plus a. So at this point, then sine squared of k x plus a is going to equal 1/2 times 1 minus cosine 2k x plus a. So then we get, plugging this back in, a squared times the integral from negative a to a. Take the 1/2 out, and we get 1 minus cosine 2k x plus a dx, and this is equal to 1. If we evaluate this, then we get a squared over 2 times the integral from negative, well, you know what, instead of even, I can just evaluate the integral right here and right now, and get, let's see, x minus sine of 2k x plus a. Let me just erase that extra quotation that I don't need. Evaluated from negative a to a. You know what, I left out the bottom term. So this is multiplied by 1 over 2k, evaluated from negative a to positive a. So this is going to be equal to 1. Then we have a squared over 2 of a minus sine of 2k times 2a times 1 over 2k, subtracted by negative a, so plus a minus sine of 2k 0, so sine of 0, and this is equal to 1. Sine of 0 is just 0. Then we get a squared over 2 times 2a minus sine 2k, or 4k a times 1 over 2k equal to 1. Then we recognize that k is equal to, as we defined above, n pi over 2a. n pi over 2a, so this is equal to, let's see, so if we multiply this by 4a, so then 4a times k is going to equal, the a's cancel, so 4a times n pi over 2a, the a's cancel, and we get equals n times 2 pi, or, you know, 2 pi, 4 pi, 6 pi, etc. That's also going to equal 0 always, so this goes to 0 as well. So we get a squared over 2 times 2a is equal to 1, or a squared a is equal to 1, or a is equal to 1 over the square root of a. And just like that, psi, going back, is equal to this expression. So then we can do the same trick we did before with sort of cosine addition or sine addition property, and we can say we can multiply everything here by cosine Ka over cosine Ka. Then we get that this is actually equal to a sine Kx cosine Ka plus a sine Ka times cosine Ka, or being equal to a times sine of k times x plus a, and then redefining a as equal to 1 over the square root of a. This is going to give us sine n pi x plus a over 2a. And if we look back on the sine term, all the way back here, so immediately the a got replaced with 2a, so automatically the 2 cancels out on the top, so we have 1 over square root of a instead, and then the x gets replaced by x plus a over 2, which is what we expected as well, and we're done with this problem. Apologies, I just realized after looking back that I might have not been entirely too clear on how I proceeded with this step. So let's look at this again really quickly. So what I did here was I multiplied everything by cosine Ka over cosine Ka. So let me do this in red. So what I did was I multiplied by cosine of Ka over cosine of Ka. So what this is going to give me is that psi of x is now equal to a over cosine Ka multiplied by sine Kx cosine Ka plus cosine Kx sine Ka. So this just goes to sine of k times x plus a, as we expected. However, this term goes down to a, and the reason why it goes down to a is because we need to recognize, okay, a is obviously a constant. K is equal to n pi, let me just look back up again. Yeah, k is equal to n pi over 2a. So for any index n, k is also a constant. So cosine of k is effectively a constant. There's nothing stopping us from absorbing this into the a term, because remember, the whole point of a is that it's supposed to be a constant in the first place. So sort of because of that, you know, there's nothing stopping us from absorbing the cosine ka. So that's how this goes down and becomes a sine k x plus a. I realized after looking back at the video that might have been a bit of a confusing step, so I apologize.